My name's John Steinke, and I teach 7th grade science at South Doyle Middle School. The handout that accompanies this video can be found at the KCS website under Student Resources tab. This is Week 2, April 6th through 10th activity packet, and today's activity is 7th grade science. If you need a printed copy of this activity, they're going to be given out at the meal distribution sites each week between 10 a.m. and 2 p.m. I hope you enjoy today's lesson. To begin today's lesson, I want to ask you a question. What do all of these images have in common? In our first image, we have an egg that is frying in a skillet. In our second image, we have a campfire that is burning. In our third image, we have a picture of iron rusting. So pause the video and think, what do these three images have in common? Well, if your answer is that all three of these are chemical reactions, then you are right on point. A chemical reaction is when the molecules within a substance are rearranged, and all three of those images were good examples. In cooking, the proteins within the egg actually changed their nature because of the temperature change. And in combustion, or the fire, the campfire, all of the wood was changing form into smoke and ash, releasing heat. Rust is when oxygen interacts with iron and changes the nature from strong and bound together to brittle and dust. And so chemical reactions are anytime molecules within a substance are being rearranged. Today, in order to look at chemical reactions, we're going to look at chemical equations. Chemical equations are the ways we use symbols to show what's happening to a substance in a chemical reaction. For example, photosynthesis. 6CO2 plus 6H2O yields glucose and 6 oxygen. When you read these, you can separate all of the letters and numbers with plus signs and arrows. The plus signs indicate different molecules inside of the reactants or products, and the arrow separates the reactants you start with from the products you end with. So what do I mean when I say reactants and products? Well, the first step to reading any chemical equation is to identify the reactants and products. Let's look at photosynthesis a little bit more slowly. Our reactants are the 6 carbon dioxide and 6 water molecules, and our products are the glucose molecule and 6 oxygen molecules. But how am I supposed to know which molecules are reactants and which ones are products in any given equation? Well, it's always that simple. The reactants are always on the left, and the products are always on the right. This way, you can know the reactants are what you start with, and they yield, that's what the arrow means, the products on the other end of the equation. When reading a chemical equation, there's a certain way to say it. 6CO2 and 6H2O yields 1C6H12O6 and 6O2. If you know the names of these molecules, then you can just say those. 6 carbon dioxide and 6 water yield 1 glucose and 6 oxygen. Now, these letters that we see inside of the chemical equations are not just random letters. Remember that they're the elemental symbols from the periodic table of the elements. To separate these letters and make sure we know how to read them, the capitalized letter always indicates a new element. For example, carbon is a capital C and oxygen is a capital O. But if I had big C, little o, what that would indicate is a totally different element called cobalt. Whenever you see a full capitalized letter, that means that there is a new element. So, when you're looking at the letters, that's what those mean. But what about all the numbers? Well, the bigger numbers at the beginning of each molecule tell you how many of that molecule there are. They're called coefficients. For example, 5H2O means 5 molecules of water. 5 is the coefficient. 2H2O means 2 molecules of water. And H2O just means 1 molecule of water. There's no coefficient, which means there's just 1 molecule. But what about the small numbers? Well, the small numbers that trail after each element within a molecule tell you how many of the element are in each molecule. It's called a subscript. When I look at H2O, there are 2 hydrogen, and there's 1 oxygen. Now, a lot of kids will get confused. They'll see the 2 before the O and think there are 2 O's, but there are not. Remember, the subscript always comes after the element it's attached to. So in H2O, there are 2 hydrogen and 1 oxygen. Now, what can we do with all of these things? Well, we can break down whole chemical formulas using what we know about each of these subscripts, coefficients, and elements. Look at this equation. 3C2I4 plus NaCl2. Now pause. Why did I say C and I on the left and C and L on the right? Well, I included this example because it's one that can confuse a lot of people. When we're looking at elements, sometimes we can't tell if it's a capital I or a lowercase l. I knew that that was an L on the right because it's sodium chloride, which is a very common molecule. And I knew that was an I on the left because it was separated from the C. You may not know all of these things off the top of your head, so when reading chemical formulas, it's important to either have memorized your elements or more realistically to use a periodic table. That won't be necessary today, as I'll make sure that every example that we're using isn't one that's going to be confusing like that. But I did want to point it out so that we have to be careful about which elements we're reading. Now let's forget all of that for a second and break down this chemical formula. How many molecules of C2I4 do I have? Well, when I look at my example, I see that I have a coefficient of 3, which means that I'm going to have, if I can get the slide to change, 3 molecules of C2I4. Okay, well, how many molecules of NaCl2? Well, there is no coefficient, so that means there's just 1. After that, I'm going to break down how many of each element are inside of those molecules. So how many carbon do I have? 6. Now, I might have just confused some of you, but let me show you how I got that. If I take my coefficient of 3 and my subscript of 2, that means I have 3 molecules of C2I4, and each one has 2 elements of carbon. 3 times 2 is 6. So that means my answer is 6. I do the same with the iodine. There's a subscript of 4 and a coefficient of 3, so I have 12. When I go to the other side, there are no coefficients, so it becomes a lot easier. I only have 1 sodium and I have 2 chlorine. Let's try another example. NaC5H3O3. How many molecules do I have? Well, I have no coefficient. That means I only have 1 molecule. Well, how much sodium is in each molecule? 1. How much carbon? I see a subscript of 5, so there's 5. How much hydrogen? 3. And how much oxygen? 3. Now remember, in order to find these numbers, what I did was I looked at the subscripts. Sodium had no subscript, so there's just 1. Carbon had a subscript of 5, so that means there's 5. Hydrogen had a subscript of 3, which means there's 3. And oxygen had a subscript of 3, which means there's 3. There was no coefficient at all, which is why I didn't have to multiply anything. Looking at this example, 4Br2U6H2. How do I break this down? Well, the first thing I do is see that I have 4 molecules of Br2U6H2. Then I break them down by what element. I have 8 Br2, I have 8 bromine, Br, because 4 times 2 is 8. I have 24 uranium, because 4 times 6 is 24, and I have 8 hydrogen, because 4 times 2 is 8. One more time, where did I get all of those numbers from? Well, bromine, 4 times 2 is 8. And for uranium, 4 times 6 is 24. And for hydrogen, 4 times 2 is 8. Once you've had enough practice with these, you should be able to break all sorts of equations down. But then you'll come across some that look like this, and they have parentheses. What do I do with the parentheses? Well, first I'm going to write down how many of each molecule I have. I have 1 molecule of PbOH2, and I have 2 molecules of hydrochloric acid. So what do I do now that I'm trying to break them down by the number of elements? Well, for Pb, it's simple, it's just 1, but it does get tricky with that parenthesis. In math, whenever you're multiplying across a parenthesis, you multiply to everything inside of it. And that's what we're going to do here. 2 times the 1 oxygen and 2 times the 1 hydrogen. So that means I'm going to have 2 O's and 2 H's. On the other side, I have no subscripts, which means there's only 1 H and 1 Cl. But my coefficient is 2, meaning I have 2 of each of those things. Once you get the hang of it, you can break down entire chemical equations and chemical reactions without a table. If you separate your reactants from your products, then you can break them down one at a time. In this equation, my reactants are my 6 carbon dioxide and 6 water, and my products that are yielded from my reactants are 1 glucose and 6 O2 molecules. If I broke them all down individually, that would be 6 carbon on each side 18 oxygen and 12 hydrogen. Now hold on, where did I get 18 oxygen? Well, it's important to see that right here, 6 times 2 is 12, and 6 times 1 is 6, and 12 plus 6 equals 18. And that's how I got that on both sides. You have to make sure you're tallying all the molecules inside of the reactants and all the molecules inside the products. But then why wouldn't I have 12 carbon? And why wouldn't I have 36 oxygen and 24 hydrogen? That's because I don't count them twice. You don't count the ones on the left and right because those are separated by the chemical reaction. Those products at the end are the exact same elements as the reactants at the beginning. So counting them twice doesn't make sense. They're the same elements that have been rearranged. Reading chemical equations helps you to understand what's happening to molecules inside of a chemical reaction. By using these skills, you can even spot a chemical reaction and see if there's any mistakes by checking the number of reactants and making sure they match the number of products. That's because they should always obey the law of conservation of mass. But what's the law of conservation of mass? Well, that's honestly the skill we would love you all to build towards. If you remember, each of these skills, as we read chemical equations and broke them down, was so that we could learn back in August and September about the law of conservation. The law of conservation states that the mass of a system must remain constant. Nothing's going to be created or destroyed. And I hope these two images will help you see that. Here, let's see on the balance scale, 1 oxygen and 2 hydrogen. If they were our reactants and they reacted to form water, H2O, we see that nothing was actually created or destroyed. We have the same pieces, but they've just been rearranged. And we can see this with something else that we use in our daily lives, a candle. If you light a candle, it appears as though some of it is going away, it's being destroyed. But actually, it's just changing form. It'll turn into smoke and vapor, which is one of the reasons why you can smell it throughout your entire house. All of these things are the law of conservation of mass as an example. And hopefully in future activities, you'll be able to test this law along with your skills of reading chemical equations. Thank you so much for allowing me to teach you this lesson today. If you have any more questions, please reach out to your local schools. Have a great day.